Good afternoon, everyone. I'm just going to briefly respond to Veritasium's really nice video uh, where he admits to being partially wrong about what he said regarding how electricity really works. But he's still more wrong than he thinks because he didn't use quantum electrodynamics. Now, in short, in Veritasium's video, he creates an experiment or recreates an experiment done by the channel Alpha Phoenix, where that channel used a kilometer of good old-fashioned doorbell wire to simulate the circuit on a large scale. Veritasium did that on a smaller scale with help of someone at Caltech. And both of those experiments found something that comports with what quantum electrodynamics would predict. A small initial current followed by a much larger real current once it had time to go around the whole circuit. But current doesn't really go around the circuit. That is a misconception. What you need to understand is what this book by Richard Feynman, the Nobel Prize winner that came up with quantum electrodynamics, the full real theory of how electricity and magnetism work, says on page 85. So now I present to you the three basic actions from which all the phenomena of light and electrons arise. A photon goes from place to place. An electron goes from place to place. An electron emits or absorbs a photon. Each of these actions has an amplitude, an arrow, that can be calculated according to certain rules. Now, calculating it according to those rules is not simple. It takes a book this big to begin to do it, and it is, let me show you, it's, oh geez, just like in my original video, it is so much complication to even begin working on it. Tons of calculus, lots of Feynman diagrams, all sorts of stuff. So you would think, well, of course, use classical electrodynamics like you would find in this book, the standard Blue Jackson classical electrodynamics book. And the truth is, when you drive it down to what Richard Feynman said, quantum electrodynamics gives an explanation that is much simpler and more straightforward than what classical electrodynamics gives. For example, the phenomena of this neodymium magnet holding this piece of metal is explained by quantum electrodynamics as well as classical electrodynamics. But to use classical electrodynamics, you have to imagine fields coming out of this and inducing fields in this, and then they stick together. But why do they stick together only when they are very close together, right? When I'm holding them this far apart, I feel almost no attraction. But when I hold them really close together, it becomes almost irresistible attraction. This is because the probability that the electrons emitting their photons in this thing will affect the electrons that could react to the electrons in this one depends on the distance between them. And when you work out all the complication in quantum field theory, the probability of interaction between these two systems depends on how close they are together in a way that gives rise to what in classical electrodynamics is called the inverse square law. So if we just dispense with all of that calculation and think about the inverse square law in terms of the probability of interaction, then his two wires that are a meter apart have some small but measurable probability of interaction between them. That explains why you get a tiny little bit of current as soon as you close the circuit, but you get most of the current, you get most of the energy once the circuit has had time to fully establish, because the electrons in the wires that are a meter apart are much closer to each other. So, as Feynman said, they can emit and absorb photons from each other much more easily. Their fields can interact much more readily than the fields between electrons in a wire, electrons in another wire that are a meter apart. Comparing interatomic distances and the inverse square law there creates an almost irresistible interaction, whereas a meter apart, it's quite resistible. So, as I said in my original video, he's partially right, partially wrong. He's still partially right, partially wrong. But classical electrodynamics are good enough for most things. But paradoxically, to analyze this problem using classical electrodynamics is even harder, because in classical electrodynamics, you have to think either there's interaction or there isn't. Either there's a field or there isn't. And then you have to do all sorts of computerized computations, like he shows someone actually did in the video, to get an answer. Which, with quantum electrodynamics, there's always some probability of anything happening. It depends on the distance between the electrons. So thinking that two objects filled with their electrons a meter apart could influence each other directly is no mystery. Of course they can.